If you haven't done so yet, make sure you pause the video and try to solve the question on your own first before listening on. We can begin by drawing a picture of the scenario. So here we have the solid uniform disk at the top of the ramp. It's going to be released from rest and it's going to roll down the ramp without slipping and reach the bottom, and we have to figure out how fast it's moving at the bottom of the ramp. And then we've marked the length of the ramp with a capital L. And we can use the principle of conservation of energy to solve this. So let's take a look at that. So according to that principle, the total energy that is present at the bottom of the ramp will equal the total energy that's present initially at the top of the ramp. Now we can actually eliminate a few of these energies. For example, the disk starts from rest, and that means that its initial speed is 0, and therefore its initial kinetic energy is 0. Now we've put two different types of kinetic energy. There is the translational kinetic energy, which involves objects that are moving in a straight line down a ramp, for example. And then there's the rotational kinetic energy, which involves objects that are spinning or rotating. Now notice that this ball or disk, as it rolls down the ramp, is moving both translationally and rotationally, because it's moving in a straight line down the ramp, but as it's moving, it's also rolling along. Now, initially, because it's released from rest, neither of those types of kinetic energy will be present, so we can eliminate them from the equation. But certainly when the disk reaches the bottom of the ramp, we're going to have both translational and rotational kinetic energy, so we have to leave those both in the final side of the equation. When the object reaches the bottom of the ramp, it's no longer going to have gravitational potential energy because it's not lifted off the surface of the ground anymore. So we can actually eliminate the final gravitational potential energy. And so the equation simplifies as follows. Now, on the final side, we can plug in the expressions for the kinetic energies. The translational kinetic energy will be 1/2 times the mass of the disk times its translational speed squared. The rotational kinetic energy is 1/2 times the moment of inertia, or rotational inertia, times the angular speed squared. On the right-hand side, we have the initial gravitational potential energy, which is the mass times g times the initial height, which we can just call y for now. And maybe we can come over in the diagram and mark that height as y. Now, there is a table in the textbook that gives us the value of I, which again is the moment of inertia, for various objects. And for a solid uniform cylinder or disk, which is exactly what we have in this problem, the moment of inertia is equal to 1/2 times the mass times the radius of the disk squared. So we're going to substitute 1/2 mr squared into the moment of inertia of this equation. Now, one of the tricky things about this equation is that it includes both the translational speed, v, and the angular speed, omega. And we're not going to be able to solve for both of them simultaneously. So what we're going to do is solve for v first, and then later we'll get the angular speed, omega. And in order to do that, what we have to do is make a replacement for omega. And to understand that replacement, we can come over here on the side, and we know that the translational speed is equal to the radius of the disk times its angular speed. If we divide both sides of this equation by r, the r's would cancel out on the right-hand side, we can see that the angular speed, omega, is equal to translational speed divided by radius. So we're going to substitute in v over r for this omega right here. Notice that it's still squared. Now when we square a fraction, we're going to end up squaring both the top and the bottom of the fraction. So the top is going to become v squared, and the bottom is going to become r squared. And what's interesting there is that the r squared that's colored in red right here multiplied by the r squared that's colored in blue, they're going to cancel because one's in the numerator and the other's in the denominator. So we can actually cancel out those r squareds. If we look carefully, we can also cancel out the mass because it appears in the first, second, and third term of this equation. So we can basically divide everything by the mass, which cancels it out. And so now we have 1/2 times v squared plus, now we have 1/2 times 1/2, which is 1/4, and there's still a v squared there, and that's going to equal g times y. These are actually like terms right here. We can find a common denominator and call this 2 over 4v squared plus 1 over 4v squared. Those will combine to make 3 over 4v squared. And that's going to equal gy. We can multiply both sides by 4 so that the 4's cancel here, and then divide both sides by 3. So we'll have 4gy over 3. and then we'll take the square root of both sides, and this will change the v squared into just v. So we've successfully isolated v. We are almost ready to plug in the known values. We know g is 9.8, but we don't know the height y yet. But if we look at this triangle here, we notice it's a right triangle, so we can use some trigonometry to solve for y. For example, we know that the sine of the angle marked theta would equal the opposite side, which is y, divided by the hypotenuse, which is L. We multiply both sides of this equation by L, and we can see that y, that height, will equal L times the sine of theta. So let's plug in L sine theta right here for the y. And now we can go ahead and plug in the known values. So once again, g is 9.8. The length was given to us as 4.5. And then we know that the sine of theta is going to have to be the sine of 15 since theta was given. And then we'll divide this by 3. So you can pick up your calculator and very carefully plug this in. Make sure your calculator is in degree mode. When you do that, you should get 3.90 meters per second. So this is the correct answer to part A. For part B, the angular speed, we said earlier that angular speed is equal to translational speed divided by radius. So all we have to do is take the translational speed that we just figured out and divide it by the radius of this disk, which is 0.25 meters. And when we do that, we get about 15.6. The meters will cancel and leave behind just a radian, and then we still have per second there, so it's radians per second. So this is the correct answer to part B.